All right, good afternoon, everybody. Welcome back.
Good afternoon.
Yeah, finishing up week 3 here. So we are flying through this course. Week 3, next week is the halfway point, week 4 out of 8. The good news is, at this point, we've gotten through most of kind of the core kernel of fundamental concepts about assembly language and microprocessors. There's a lot more that we're going to go over and learn and work with, but what you've done so far is kind of like the essential kernel of skills that you'll be using for the rest of the course. And so we're kind of at a bit of a plateau right now, and then we're going to start building on top of that. But we're at a place where we have a pretty good foundation to build from. Um, I've heard a lot of things about assembly. You've heard bad things about assembly? Yeah, most people will say bad things about assembly. I think it's kind of enjoyable, because it's so, kind of what you see is what you get. There's no particular weirdness about, oh, you got to have a semicolon here, or something like that. It's like you say do this and it does this, and if it's a totally silly thing to do, it's okay, it does it anyway. Um, so that's cool to hear. Yeah, nice that people are enjoying it. Um, I think it's a lot of fun, and I always look for excuses to do assembly language. Um, Definitely a different experience from Java for sure. I mean, Java is so kind of well structured, and you have to have everything just right. And yeah, that's true in assembly language, but it's a different feeling somehow.
Would you have any recommendations for what's a good place to start if you wanted to learn a more complex assembly, like after this class, like maybe an ARM assembly or an x86 assembly?
Well, so ARM is a really good way to go. ARM is, the most popular architecture on the planet. It's like 99.9 some percent of all CPUs are using an ARM architecture. You can, if you have a Raspberry Pi, it's like, a $20 computer or something like that. You can do assembly language on that, and that's all ARM based, but it's in a Linux operating system, so you've got your tools, GDB, things like that. That could be really fun. I think that would be a really fun course to teach actually sometime. Is ARM assembly language on a Pi. But that's one way to do it. You can play around on an Arduino and play with the assembly language in there. That's not particularly well supported. Most Arduino stuff is done in a variant of C++. Um, but ARM is not all that much higher level than what we're doing on the PIC. ARMs are still reduced instruction set computers. And if you want to go to a complex instruction set, probably you're going to go to x86. And that can be a big leap. But if you're writing code yourself, it doesn't have to be. You can work with, whatever subset of the thousands of x86 instructions there are, and sort of build up from there. Um, Another option is go old school. Get yourself something like a Z80 emulator and play around with Z80 assembly language, and that can be fabulously fun. It's 694 instructions, I think, so it's definitely not a RISC machine. Um, but it gives you a flavor of what you can do when you have more complex addressing modes, things like that. And I love the Z80. That was my favorite processor for a long time, and I recently just built a standalone Z80 training board that I hope to use someday for a class. So that can be fun. There's tons of emulators out there and assemblers and tool chains like that. And once you're playing with something like a Z80, you can start, if you really want to get ambitious, porting like CPM and bringing over some of the old games from the 70s, Star Trek and Wumpus and things like that. And so you could have a lot of interesting directions like that. Let's see. Yeah, and video games. Yeah, actually, so same kind of thing. If you want to get deeper into hardware and different instruction sets, right? So Z80, 6800s, processors like that. That's what you find in the arcade cabinets from the 70s and the 80s. And
6502.
yeah, 6502, big one. And those are all, 8-bit processors, so they're not, monstrous to try to grapple with the way like an x86 might be kind of overwhelming at first. But there's lots of good legacy stuff out there. People have, documented the electronics for, say, an old Gyrus game or Space Invaders or things like that, and that could definitely be fun. But the pick's pretty good, and learning pick will definitely help you if you wanted to play with ARM. Like I say, it's not that big a transition because they're both RISC machines. Um, but I think Raspberry Pi assembly language would be fun to play with.
I thought ARM was a little bit of both.
Um, well, so ARM is not a single architecture from what I understand of it, and I'm not sure I have a perfect understanding of it. But it's kind of a class of architectures. But I think they're mostly RISC-ish. They might have more instructions than the PIC, but it's the real. We're going to start talking about this today, actually, in lecture. The real kind of demarcation of a RISC versus a SIC, I think CISC has to do with the clocking, and how much can you do in one clock tick. And when you have a processor that's really geared towards doing something every clock tick, you're probably looking at something closer to a RISC machine, and that's what ARM architectures do. And we're going to look at clocking of instructions today when we learn about delay loops, which we'll be using in Lab 3. So we'll talk a little about pipelines and branch prediction and good stuff like that. All right, so I graded homework 2, and I posted comments on that. I mainly looked at 3 questions, the 3 most programming questions, which was 29, 30, and 31. I glanced at 18, 20, 23, 25, 29, those first 4, which were more kind of thinking about and assessing different questions. But then I actually graded the code for 29 through 31. And those were about loops. And people didn't seem to have any trouble with that. But yeah, so 2 comments to make. So the first one, I'll just say, loop isn't an instruction. So let's suppose you write an infinite loop like this. Loop increment file register 80, and then branch to loop. All right. So how many instructions is that? Let's play around with this. All right. So I've got my small little infinite loop here. Let's go ahead and build that and look at the disassembly listing. It's a single instruction, right? That instruction for branch to loop got stored at location 0, and it occupied 2 bytes, which were filled with D7 and FF. And the instruction is branch 200. And suppose I did this. Right? How many instructions is this program going to be? How many bytes worth of instructions? It's going to be 1 instruction. Build that up. It's still just a D7FF. All of this stuff up here, nothing to do with the final bits that you see in the memory of the processor. Right? These are used by the assembler, right? MPLAB, when I hit this button which says go ahead and build my project, when I say branch to loop, it will say, well, where is loop? Well, loop is the address of wherever the next instruction is stored. The next instruction is this branch that's stored at location 0. So loop means location 0. When I say branch to loop, it's the same as branch to 0. So these labels, right, don't actually compile or assemble down to ones and zeros that you see in the memory of the system. And so that brings us to question 31, which is what's the smallest loop that you can possibly make? And this is pretty much it. This is just, one instruction that says branch to my current location. And so 2 bytes, 1 word, that's the smallest program that you can make that will loop forever. And you don't have to do anything in here. Usually if you have a loop, you're doing something inside, but you don't have to, right? If you just want to kind of sit there and spin and burn up electricity, that will do it for you. And if you're looking for shortest in terms of number instructions, this is 1 instruction. If you're looking for shortest in terms of number of bytes, suppose I say go to instead of branch. Well, it's still 1 instruction, but guess what? It's 2 words. It's 4 bytes. Because a go to is one of these funny instructions that actually takes 4 bytes to code, not just 2. And we're going to talk about the coding of go tos later on, along with calls and moveff. So if someone asked you for the shortest number of bytes, you would want to use a branch instead of a go to. All right. I haven't looked to see how many people turned in Lab 2, but any parting questions on Lab 2?
So my new experiment was basically trying to set up a conditional like we did the last lecture, where it's much more clear with like an if, a then, an else, and a continue. So
Okay.
conditional is not opposed to continue. Is that something we're generally going to be doing instead of just using a single branch at 0, even though it probably uses more memory?
Yeah, so we're going to talk about Lab 3 later, and Lab 3 is really just a big complex if statement. It's the traffic light controller. And we're gonna write out some pseudocode for that, but it's gonna be basically a bunch of if then elses. And so sometimes, like when we talk about delay loops, we're just gonna do a simple conditional branch if 0 or branch if not 0. But a lot of times it's gonna be more complex than that. Let's see, question. Pin 7 is the most significant bit, and 0 is the least. So are you talking about pin numbers or about bit numbers? And I'm thinking you mean bit numbers, because there is no pin 7. I mean, no pin 0. Generally, bit 7 is going to be more significant than bit 0. That's not 100% guaranteed to be, what you find on every planet in the galaxy. But usually, when you have a binary number, this is called bit 7. If it's an 8-bit number, this would be bit 0. Almost always, the least significant bit's going to be on the right. Most significant's going to be on the left. And certainly, everything I do in this class and everything I do in my CS classes will follow this convention, where we number the more significant bits with higher indices. Let's see, I expanded on the first experiment, and then my MP lab wouldn't let me trigger pins until I restarted it twice. Is that just the program being weird or what? So if you're expanding on the first experiment, hopefully you started a brand new project in MP lab. If you didn't, then all bets are off. So even if you're modifying the existing code, make sure that you close your current project, create a new project, go through all that setup with P18, F1220, and so on, and then make a new source file, paste your code into there, and go on from that. That would be my first guess for weirdness that you might encounter. Looks like other people have encountered weirdness. I have not seen any sort of kind of habitual hiccups in MP Lab the way we do with like the Verilog software. in 250. MP Lab seems to be pretty solid. It's a well-supported commercial product. So we shouldn't be finding hiccups in there, but if you find things like that and you can reproduce it, definitely come by lab hours and show me, and we can either figure out what's going wrong, or, you know, if there's an actual issue, we can file a bug report. Alright, so talking about ports, I've seen somewhere 0 is the most significant. Yeah, okay, so yeah, we'll stick with 7 is most significant. And yeah, definitely close all your projects before you compile a new experiment. That's a good idea. Oh, and you had no issues with Verilog. Cool. Yeah, I mean, I think you were in my 250 class. You saw how many times I had to restart the software during a lecture because it would just keep crashing. But maybe that was me. All right. Well, bunch of things I want to go through today. Let me go ahead and start with an attendance ping. So go ahead and pop me a direct message. Let me know that you are here. And stuff I want to go through today. We're going to start off by talking about stacks. And if you're a CS student, you will know all about stacks either from your past or in your future, because it's a common data structure in computer science. So if you haven't encountered this yet, this will be sort of a first intro to stacks. You may have talked about it in 121. I'm not sure. Also, if you play Magic the Gathering, there's a stack. When you play cards, you put effects on a stack and then you pull them off in reverse order. That's a stack. So everything that we're going to talk about, you can just think about how you resolve spells in Magic, and it's the same concept. So we're going to talk about stacks and about doing calls and returns. We've danced around this a little bit so far, but how we can basically implement functions in assembly language, and that's going to be really useful for keeping our code clean. And Lab 3's code is not, the worst thing in the world, but if you don't organize it well, it can become a big spaghetti ball of stuff. So being able to call functions and return from them will help us keep our code clean there. And then I want to talk about instruction timing, and this will be a little bit of the stuff we talked about with respect to ARM a little while ago. Clocking and instruction timing and pipelines and good stuff like that, and that will let us understand how we're going to implement this 2-second delay in our code in MP Lab, which will be part of the traffic light system. And then I want to go through Lab 3 in detail, talk about some pseudocode for that, and get you a head start on coding that. And then, depending on how much time we have left, well, I'll talk about coding of gotos and moveFF, some of these 32-bit instructions. And then if we have time after that, we're going to start talking about interrupts. If not, then we'll start interrupts on Tuesday. And interrupts will be the next sort of big concept in what we're talking about. And interrupts are key to programming, not just microprocessors, but if you do any programming in a larger environment, like if you're writing an Android app, or a GUI or something that is part of a game engine, you're dealing with interrupts, either software interrupts or hardware interrupts. So it's a pretty fundamental concept, and that will bring us into our next lab 4 next week. So a bunch of stuff to go through. Let's start with talking about stacks and calls and returns. And so what's the main concept of a stack? Picture, stacking things up on a table. All right. So let's say you this is harder to do on camera because I can't stack things on my desk. Let's do the buffet example. So you go into a food buffet, right? And there's a thing next to the food area that's filled with plates, right? And the plates are stacked one on top of another, and they're kind of spring-loaded from below. And when you come into line, you take the top plate, and that's what you put your food on. This is when we used to go out and eat in public. Um, and when you take a plate off the top, what happens? The plates below it rise up magically, right? Because they're spring loaded, and now there's a new plate sitting on the top of this stack of plates. And you take your plate and you put food on it, and the next person who comes along takes the plate that's now on top of the stack and starts using that. So we have, you know, this thing that holds plates. This is a stack of plates. This is the top of the stack, what we just call TOS. And if I grab this plate, well, all these plates move up, and now this plate is sitting up on the top of the stack, and so on. And if enough people come along and keep taking plates off the top, what happens to the stack? Eventually it becomes empty. And if someone comes along and tries to take a plate off the empty stack, it's an error condition. It's called a stack underflow. All right, well, periodically, somebody comes out from the kitchen with an armful of plates they've just washed, and what do? They put them into the stack. So they put a plate here, and all the plates move down. They put another plate, and all the plates move down. They put another plate, and all the plates move down. And let's say they had 10 plates, and they put those 10 plates on here, and the stack moves down. Well, which plate is on the top of the stack now? It's the last one that they put in. So the main thing to remember about a stack is it has the following behavior. The last thing that you put in is the first thing that you take out. And so this is called a LIFO, last in, first out. So if I were stacking pens, right, I would put this pen down, and then I put this one on top of it, and I'd put this one on top of it. And now if I go to take a pen, I take this one, the last one that I put down. And now maybe I put this pen on top, and now I put this pen, and now I put this one. And now if I take a pen off the top, it's going to be that last one that I took. Well, if I take another pen, what's it going to be? The pen that's currently on the top was the one that I had previously put down last. So I grab that off the top of the stack, and then this one, and this one. And this last pen that's left here, that's the first one that I put on the stack. So this is also a first in, last out. The very first thing I put on here, that's the last one I'm going to take, because all these other pens are going to go on top of it. And I might take two of them off, and I might put another one on and take it off and put another one on. And this poor one is sitting down here at the bottom, right? That's the last one I'm going to take off. And I only get to that after I've taken off everything that I put on after that. And now if I take one more pen, it'll be that. And now if I try to take a pen, it's an error condition. So that's kind of a mechanical view of what a stack is. Why is this interesting in computer science? Because we kind of work with stacks. That's kind of the way that our brains seem to work. Whether that's how they're biologically wired or how we're taught to use them, I don't know. But here's an example of stack-based processing in daily life. So you sit down to do your homework, right? And you start, reading through the questions and writing some code, and all of a sudden your phone makes a noise, and you've got a message, right? So what do? You stop doing your homework and you start looking at your phone, all right? And while you're looking at your phone and you're, updating a post or something like that, there's a knock on the door. Well, what do you do when there's a knock on a door? Do you continue working on your phone? Probably not. Do you go back to doing your homework? No. You go and you answer the door, right? And there's someone, at the door selling something, and that's very exciting, and you talk to them. And your phone and your homework, they're kind of like, down in the stack. And you're talking to the person on the door, and they sell you something, right? Well, you don't have any money with you, so what do? You go and you get money. And the person is standing there on the door waiting for you to come back and complete this sale. and your phone is still sitting there in the middle of a Facebook post that you were making, and your homework is still sitting there waiting on question one, right? And you get your money, and you give it to the person at the door, and they give you the vacuum cleaner that you just bought, and now you go back to your phone and update your post or whatever it was that you were doing. And maybe while you're doing that, suddenly you get hungry, and so you pause what you're doing here and you go off and you get some food, right? This is last in, first out. The last thing that got your attention is the first thing you're going to deal with. And the first thing that you put on your stack, which was your homework, that's the last thing you're going to get to. Okay? That's a stack-based behavior.
It resembles having ADD just a little bit.
Exactly, yeah. And different people have different levels of stacks that they can maintain. And you know, you may find that you finish something here and it's like, what was it I was doing before, you know, and you can't remember anymore because you had a stack overflow. You ran out of storage space in your stack. But this is how most of us work. This is how we surf the web, right? You start on one page, you see something, you click on it, you read something else, you see a link there, you click on that, and eventually you're 20 links from where you started, and you've got, what do you have, a back button. You hit that little left arrow and it pops your stack and you go back one level. And you continue reading that page and then you hit the back arrow and you go back to the previous page. So stacks pop up all over computer science, right? And we use them when we make web browsers, you know, hyperlink text, things like that. And we use them when we make functions. And this is the main reason we're interested in stacks in this class, is it's going to let us do something like, you know, writing a function in C. And how do these pop up in functions? Well, it's just like, you know, doing your homework and then dealing with your phone. So typically we have some main program and we do a few things and then we want to, you know, call some function which says, you know, get input. So we call some get input. And over here is, you know, a function that prints a message to the user and says, hey, give me some input, and the person types something and it does something, right? Well, when we say call get input, what happens? Our computer is not going to just go ahead and execute the next instruction. It's going to change and start executing code over here. So if this was written in C, all of these C instructions get executed until you say return. And when you say return, what happens? Well, you go back to the thing after the call instruction. Now in C, we don't say call, we would just say get input, but I'm putting in call to be explicit. And then maybe we do some other things and we want to get more input, so we say call get input. And that's going to make another call over here. But this time, when our get input code says return, it doesn't go back here, it comes back over here. So the cool thing about a call instead of a goto is when we make a call, it remembers the next instruction's address. And when we say return, that's the address that it goes back to. Okay, basic function call and return behavior. Sure. Okay, so you've got a main program, and it's executing some instructions. Sorry?
The call versus go to, so like a call.
Yeah, so when we say call get input, we jump down here to this other section of code, but the system notes where we made that call from. It says, hey, you made that call from right here. And now when we say return, the CPU will say, okay, let's go back to where we made the call from. That was right here. Okay, it comes back here. Whereas if we said go to get input, we simply start executing this code and there's nothing that remembers that we did our go to from here. So there's no way to get back to this next instruction. Unless, you know, we put a label here and at the end of this we said go to, you know, that label, which is right here.
Okay, that makes sense. Thank you.
Sure. Now the downside with a goto is that if we wanted to call this function again and we said go to get input, and we got down here and it said go to that label, it's going to come back here. What we really wanted to do was come back here. So we don't always want this to go back to the same point. We want it to go back to a place based on where we were when we jumped over here. So that's what the call instruction does. We say call get input, and it says, oh, okay, you made that call from right here. When you say return, it says, okay, let's go back to here. So calls need to remember where you were so that you can get back there. And one way to do that is to just, take this address of the next instruction and just save it somewhere. But the problem with that is, what if you have a call inside a call? What if this function ends up making a call somewhere and executes some stuff and then does a return? Well, you need this return not to go back here, but to come back here. And then this return needs to go back here. So you need to keep a collection of addresses. Every time you make a call, you need to remember where that call was made from so that your next return will go back. And the way we do that is to use a stack. So each time you make a call, you take the return address, you push that onto the top of the stack, and then each time you say return, you take the address that's on the top of the stack, that's where you jump back to. Let's see, what would happen at the end of the branch if you used goto? So if I said go to get input, right, you can't use return if you haven't used call. Return means go to the address that you saved when you said call. So if you didn't say call and you said return, you get a system error. The CPU resets itself. If I say go to some address, then, I'll go to that address, but that's always the address I'm going to go to when I get input. So if I call get input here or here with a goto, it's always going to return to the exact same location. And that's going to be a problem in terms of calling this from multiple places and wanting to come back to the place after that call. So let's make this a little more specific. All right, so let's say we have some code like this. And let's say down here at line 100 we have our function called sub1, and that does something, and at 110 it says return. And let's suppose that at line 120 we have our function sub2, and that does something, and it also says call sub1, and then it does something, and then 150 does a return. All right, so my main program, and this is like pseudocode. This is not assembly language, but it's kind of like, I'm thinking of like, I'm just numbering these statements so I have a way to refer to them. So I'm going to call sub1, I'm going to call sub2, I'm going to call sub2 again. And then, I'm going to do something here. And sub1 just does something and returns. Sub2 does some stuff, and then calls sub1, does some other stuff and returns. So let's take a look at our stack as we're executing this program. So our stack is originally empty. Okay, I'm just assuming that. So we do some statement at line 10, some statement at line 20, and then at line 30 we say call sub1. So what do you think we should push onto the stack when we make this call? Sub1, what about, well, so we could put sub1 on there, right? We could save 100. But then when sub 1 says return, where would we like to return to after that first call to sub 1? Here's a call to sub 1. Sorry?
We return to main after we're done with sub 1.
What line of main?
Line 40.
Line 40, right? Generally, when we make a call, our hope is that when the thing that we called returns, we end up at the next instruction, whether this is C or assembly language or something else. So we'd like this return to come back to line 40. So the ideal thing to save on the stack when we make this call is a 40. Right? We save the address of the next instruction. We jump down to sub 1, we do some stuff, and then when we say return, what do? We take the thing on the top of the stack, and we pull that off, and that's where we go to. So now we go to line 40, we're executing this statement. And now we're going to make a call. Go ahead.
Without jumping like too far ahead here,
Mm-hmm.
but if you say have some recursive function or one function, you call one function and then that function calls another function.
Mm-hmm.
After you're done with the second call of a function, you return to the first function and then
Right.
you return to the function before that.
That's
So
correct.
if you say had something like, also with like a recursive function, you're just going to return to every call of that recursive function.
You're always going to return to wherever the last place was that you saw a call.
Okay.
And even if you're recursing, if you're calling yourself, you're still just going to return to that last place that you made a call from. But your whole call history will still be there except for that last return.
Okay.
So we're actually at a place where we're going to do that. So let's say we're at line 50. We're going to call sub 2. What should we save on the stack? Where would we hope to return to after we call sub 2?
Line 60 main.
Line 60. Does everybody see that? We're going to call sub 2. We don't know what sub 2 is going to do. It's going to do something. But when it's done, it's going to say return. Where do we want the machine to go? Next statement, line 60. So in order to make sure that the return comes back to line 60, we're going to put a 60 on the stack. Now we're down here in sub 2. Sub 2 does some stuff, and now it's going to make a call to sub 1. Line 130 is calling sub 1. What line do we want to return to after sub 1 is done?
We're going to return back to sub 1, 110 after we've called.
So we're in sub 2.
We're going to return to line 130 in sub 2 after
Yep.
we complete sub 1.
So we're in sub 2, line 130 is a call. When we're done with that call, we want to return to the next line, which is 140. Does that make sense? So anytime that you make a call, all you got to do is remember the address of the next instruction and make sure that that's saved somewhere. So if line 130 is making a call, let's save 140. If line 30 is making a call, let's save 40. If line 50 is making a call, let's save 60. This is called the return address. And every time that you call a function, we're just going to save the address of the next instruction. In this case, the call is on 130, so we're going to save a 140. But where do we save that? We're going to save it on our stack. So we're going to put that as a new plate on top of the stack. The 60 pushes down. This is the top of the stack. And there's our 140. And since we're calling sub 1, now we're sitting here, we're at line 100, sub 1, we're going to execute some instruction. When we say return, where do we return to? Simple, just look at the top of the stack. Top of the stack is 140, that's where we're going to return to. So we remove that from the top of the stack. So now 60 is the top of the stack, and that 140, that's the address we return to. So what just happened? We called sub 1, did some stuff, and then came back to this next instruction, 140. And then we say return. Where should we return to? I don't know. Let's look at the top of the stack. Top of the stack is a 60. Okay, we're going to return to 60. That brings us back here. And our stack is empty now. And we're going to execute line 60, line 70, and here's a call. So we're going to take the address of the next instruction, maybe it's a 90, and we'll push that on the stack. And we'll come down here to sub 2, and this will happen again. All right, is this working for people?
The idea is there.
Okay.
To figure out where you would put stack in the code is kind of interesting.
Yeah, no, I'm just after the idea right now. Just this notion that when we're going to make a function call, we want to somehow save the address of the next instruction. And rather than just, save it in some register or something, we're going to save it by putting it onto a stack so that we can have multiple calls. We can have, a 60 and then a 140, and we can save all of these things that we want to save and then pull them off in the right order.
You're probably going to get to this, but I mean, I haven't done it when I was programming in my own private time, but you can manipulate the stack outside of returns too. So like you can get, like, if you're currently in some third function and you have two functions beneath you and you just want to go back to the main function, you can remove those two functions from the stack and go back to the beginning, right?
That's correct. You can do all kinds of funny business with the stack, and we do, or compilers do. We can use it for temporary storage of locals and things like that. But we won't in this course. We'll keep things more simple in this course. And even with the pick processor being a pretty simple machine, it does most of the management of the stack for us. We don't have to look and see the next address is 60 and push that onto the stack ourselves. That happens more or less automatically. And so, yeah, good terminology. I would say that this call to sub 2, which then made a call to sub 1, that's a nested call. And nested call just means we have multiple return addresses stored in our stack. And in practice, the stack gets really big. You end up with a lot of things on there. And if you make too many calls, you can run out of stack space. You bring too many plates out from the kitchen and try to pile them up, and your container of plates can only hold, 50 plates, and you try to put a 51st plate on top, and it falls off the top and it cracks, That's a stack overflow. And that's also usually considered a system error, and your program will exit, or maybe the system will reboot. On the pick processor, the CPU will reset, and it'll go back to the beginning of your program and start executing.
Is it potentially dangerous to do all that manipulation for the stack, as in you could get side effects and stuff that happens that you wouldn't necessarily plan for?
Absolutely. But danger is a relative term, so it's not generally dangerous, but if you monkey with a stack yourself, you definitely risk the possibility of corrupting data. You risk the possibility of losing a return address that was important, or stepping on some information that was being saved, and so on. On the other hand, a lot of exploits are based on manipulating the stack. If you know what you're doing and you have malicious intent, you can go in and change a stack pointer, or examine things that are on the stack and change them, and get a program to do something different from what it was supposed to do. And there's exploits for getting around security and stuff that are based on manipulation of the stack. When we get to data structures, if you're taking CSE 222, we play around a lot more with the stack. And at university, if you take computer security classes and so on, you get to do labs where you actually go in and manipulate the stack and actually do some of these exploits and see how they work. And it's a really good way to kind of understand how all this stuff works at a deeper level, and it's a lot of fun. All right, so fortunately, we don't need to worry about too much of this on the pick. So there's an instruction called call. It's under these control instructions. And call is just like a goto. It takes an argument which says where do you want to go to. But when you say call, it simply takes the address of the next instruction and it saves it on the stack. And then guess what? We have another instruction, return, and return says, see what address got put on the stack, remove that, and go to that address. So call and return are actually pick instructions. And we can say call, some label, we can say return, and it'll work just like setting up functions in C. And this can be really useful for keeping your code cleaner. So for example, in lab 3, we're doing our traffic light control. And we know with our traffic light, we need a 2-second delay between yellow and red, right? When a car loses priority, we want their light to change from green to yellow, wait for 2 seconds, and then turn to red. And so there's different places in our code where we're going to want to do this 2-second delay. And rather than, write the code 3 or 4 times, we're going to find that it's easier to just write one function, maybe call it delay, that does all the stuff that has to happen to make this 2-second delay and does a return. And then in our program, if at this point we want a 2-second delay, we just say call delay. And this code will execute, and when it's done, it'll come back and go on to the next instruction. And so it's almost like making a new instruction, right? It's something we can plunk into our code here, and here, and here, and every time that we encounter that call delay instruction, all the code in our delay routine runs, we get a nice 2-second delay. And this is one of the recurring themes in trying to write larger pieces of code and make it manageable, is breaking it into functions as much as possible, so that we don't have 50 lines of code here and then the same 50 lines of code here and the same 50 lines of code 10 other places, and we've got 500 lines of code now to plow through, right? So we write that code once and we just call it from different locations. All right, so let's look at the details of this. And there's some homework questions that deal with these details. And on the subject of homework questions, by the way, a good place to go to ENGR270.com. So these are additional homework questions. Go under course syllabi and click on Engineering 270. If it asks you for a password, the password is Clark, C-L-A-R-C, lowercase. And here's the kind of general syllabus. There's other homework questions in here. So if you want to deal with homework questions about program flow, Chapter 4 homework. And this is like the 250 homeworks. There's pairs of problems solved and unsolved. And so these are other good resources you can use to practice some of these concepts, and you can work on the solved problem and see the solution, figure out if you got it right, and then you can work on the unsolved problem. Oh, thank you so much. Oh, someone just made me a cappuccino. Glorious. All right, so that's a good resource. All right, so details. Like everything else, this is based on special function registers. So if you go down here to Chapter 5, Table 5.2, special function registers. So the first 3 registers listed, TOSU, TOSH, TOSL. So followed by STKPTR, that's the stack pointer. So let's look at the stack on this particular PIC processor. And we can think of the stack as 31 locations. And we can number these locations 1, 2, 3, 4, all the way down to 31. And we usually start numbering from 0, but stack location 0 actually doesn't exist. It's kind of weird. And there's a stack pointer, STKPTR. And stack pointer tells you where the next thing is going to. Let's see, let me see if I can get this right the first try.
I don't want to jump ahead again here, but
Mm-hmm.
so you're able to only put 31 things on top of the stack, otherwise you get an overflow error, right?
That's correct, yeah, and that's just on the pick. Now on x86 you can use, you know, at least a quarter of your main memory for stack space if you like, I believe.
I thought some languages have like hard limits on it, like Python is 1024.
Is it really? That's a small stack. So let's take a look at the call instruction. So we'll go into the full data sheet. And the behavior of the call instruction takes PC plus 4 and writes that to the top of the stack. So call instruction takes 4 bytes, right? It's a 2-word instruction. So the current program counter, the address of the call instruction plus 4, that's the address of the next instruction. And so the first thing this does is take that address of the next instruction, save that on the top of the stack. And then it takes the address that you said you wanted to call and it loads that into the program counter, the thing that says what instruction should we execute now. All right, and the stack pointer is initialized to 0, right? So value on power on reset or brownout reset. So these are the initial values. And the stack pointer is initially a 0. So the stack pointer is location of the last thing pushed. So when you push something onto the stack, what do? You increase the stack pointer. And then you use that to save whatever value you want to push. So when you make a call to a function, first thing you do is increase the stack pointer from 0 to 1, and then you store the return address at this location 1 in your stack. Now your stack pointer is 1. If you make another call, what do? You increment the stack pointer to 2, and you store the return address at location 2 in the stack. When you do a return, what do? You look at the stack pointer, you find the return address from there, you load that into the program counter, and then you subtract 1 from the stack pointer. But like I say, we don't have to. Say again?
Could you incap or decap the stack pointer?
You can treat the stack pointer however you like. It's just a general purpose file register in the special function section. So you can load values into here explicitly. So you can inc and you can dec, but for doing calls and returns, that's done for you. But if you want to get funny, you can definitely manipulate the stack pointer yourself. but usually we don't. All right.
So the stack would be sort of like an array with the stack pointer as an index.
Exactly. And in fact, when we implement stacks ourselves in a data structures class, that's exactly what we do. We make an array and we have an integer called a stack pointer that basically indexes in that array. All right, let me see if I can find you a good source for this. So figure 5.2 isn't too bad. This shows you your stack, and it's got locations 1 through 31, and stack location 0 doesn't exist.
Is there specific memory dedicated to the stack?
Mm-hmm. Yeah, it's a totally separate area of the hardware. Let me see if it's in our data path picture. So yeah, so down here is 31 registers that correspond to the stack. And the width of this stack is more than 8 bits, right? What are we storing in here? We're storing return addresses. We're storing locations in program memory. In other words, we're storing the contents of the program counter.
It would have to be big enough to house 4096 numbers for the bits.
Exactly.
That's how much program memory we have.
Yep. So we have to be able to store at least enough bits to represent 4096 different locations. So 4096, how many bits do we need for that? This is a logarithm question.
You would need 13 bits?
12 or 13, depending on where you start. But yeah, pretty close. So a quick rule of thumb, 1024, 10 bits. And this is what we call 1K, 1024. But, you know, metric system, 1K means 1,000. So is it 1,000 or 1024? Well, it's not a big difference until you get up to, like, where you're buying a terabyte drive, and you don't get a terabyte. But we can roughly think of 1,000 as being 10 bits. And so 4,000 is 4 times as much. Well, 10 bits, if you want to have 4 times as much, that's going to be 12 bits. If you had 1,000,000, that's 1,000,000. 10 plus 10 is 20 bits. If you have 1,000,000,000, that's 1,000,000,000. 10 plus 20 is 30. So every 10 bits takes you up to 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, and so on. It's a quick rule of thumb. It usually works. But this difference between 1,000 and 1,024, that's a marketing thing. That's why when you buy a terabyte drive, it's actually only like 900 some thousand gigabytes instead of 1,000 gigabytes. Because they advertise it as a terabyte, but they actually mean a trillion bytes, not 2 to the 30th bytes. And that difference gets more significant the bigger the numbers get. So that's why your drives are always smaller than what they say on the box. All right. So when we make a function call, the return address gets pushed onto the stack. The stack pointer gets incremented. and then the return address gets saved at that location. When you say return, the value that the stack pointer is pointing to gets noted and loaded into the program counter, and then the stack pointer is decremented. If the stack pointer is already 0 and you say return, you get an error. If the stack pointer is 31 and you try to make a call, you get an error. And we can play with this. So let's make a little pathological program here that's going to do a few no-ops. Nope is just a no-op. Doesn't do anything. It takes 2 bytes to store and it doesn't change anything. So we'll do a few no-ops and then we're going to do a return, and we haven't done a call yet. So let's build this and let's go ahead and debug it. And we're sitting at this breakpoint, and let's go ahead and start stepping. Well, let me put some more stuff after here. So let's build that. Let's execute it. So we're sitting at this no-op. I'm going to step through this. And now I'm about to execute a return instruction. Well, what's going to happen? It's going to generate an error condition. And that error condition is going to cause our CPU to reset. And I can add a watch down here. So I'll add a stack pointer watch. And let's go ahead and reset our program and start executing. So our stack pointer is 0, and we're going to step a few times. And now we're going to do our return, which is a bogus thing to do, right? And look what happens. Our stack pointer becomes non-zero. This second bit from the right became a 1, and we jump back to location 0. So if you look at your data sheet, and you look at the stack pointer register, and you look at that second bit from the left, what is it? STKUNF. That's the underflow bit. That's telling you that you tried to pop from the stack and there was nothing on there. The flip side of that might be something like this. So let's just go ahead and keep calling ourselves, right? So let's reset this, compile it, go ahead and execute, and start stepping through. All right, we're about to say call loop. Our stack pointer right now is a 0. If I execute this instruction, my stack pointer becomes a 1. And I'm at this location loop, right? I've just done a call there. If I execute another call, my stack pointer becomes 2. So we make this a little more interesting. Alright, so when I say call loop, I'll jump back up to that previous instruction. That's where loop is, and my stack pointer is 1. And if I do it again, my stack pointer becomes 2 and 3 and so on. And I got a cappuccino, I can do this. All right.
By the way,
Sorry?
you can hit F7, by the way.
Okay. Yeah, that's true. So our stack pointer is 30. So if I go ahead and do my no-op and then I execute a call, what happens? My stack pointer changes to 128, and suddenly I'm back up at location 0. Alright, why did that happen? Well, what does it mean when this most significant bit of my stack pointer is a 1? That's the stack full. It's a stack overflow. So we tried to remember too many return addresses, and it threw up its arms and said, I can't remember this anymore, I'm just going to start over. So it basically cleared its stack.
That kind of sucks.
It really sucks when it's not intentional.
Get an error.
So on a program running, in Linux, a C program that just called itself, we would eventually get, a seg fault or a stack dump or something like that, and we would know what happened. But here, our program just started over at the beginning. But when our program started at the beginning, the stack pointer was not 0. And normally when we start our processor, the stack pointer is 0. So what you'll do, if it's possible that you'll get a stack overflow or underflow, very beginning of your program, first thing you do, check the stack pointer. See if these bits are set. And if they are, then you know that you're here not because your program just started, but because the processor reset, because there was an error, like a stack overflow. All right, so that's a lot of words about stacks.
That's also why you can have a stack underflow. You couldn't do that in C if you tried to do it, but it's an error down here in assembler because nothing will stop you.
Right, and you can do it in C too. Well, no, it's harder to do in C. Because if you return without pushing, it returns back to the operating system. So yeah, you're right, it's hard to do in C.
I didn't know it was possible in C. Now I want to try it.
I'm not sure it's possible because the return just says go back to the operating system. But in the operating system, which is a big C program, at some point it's at the top level, and if it tried to return, it would generate a stack underflow, and it would be a hardware error, and that would probably be a panic, like a kernel panic, and the system would reboot. So this is another thing about assembly language, right? We've got our hands inside the CPU, and it will do whatever we ask it to do. And, abnormal conditions like this, not a problem. I mean, it's just going to do what we said, and it's kind of on us. Now, when we're writing C or, certainly Java or something like that, you're in kind of a controlled environment, and if you do something wrong, something in the operating system will usually notice and will cut you off and terminate your program, for example, before you actually do harm to the operating system. So that makes this a little more fun too. All right, so two other instructions related to this, and call and return are usually the main ones that we're going to be using. But there's also a pair of instructions, push and pop. And push and pop simply take the next instruction's address and put it onto the stack, or remove whatever's on the top of the stack. I don't think we have a whole lot of use for those. But push the top of the stack, takes whatever the next instruction's address is, puts that on. It's basically a call without actually doing the go-to part. So a call is a push followed by a go-to. A push just does, saving the return address on the stack, but then it doesn't actually do the go-to. And a pop is like a return without the return. All it does is remove whatever's at the top of the stack, but it doesn't actually go to that address. And so we use these sometimes when we want to, do our own manipulation of the stack without automatically going to the address that we pushed.
I have a small question.
Yeah.
So, just out of curiosity, what's the point of a no-op if it doesn't have a use? Like, how is it applied?
So, if you go back really far to the old days of doing development, we didn't have assemblers. You had to assemble everything by hand. And, when you write your code, you're saying, branch here, branch there. You're specifying addresses in memory where you want to branch. Well, a really bad experience would be you write a bunch of code and it's, 200 lines of machine code, and you suddenly realize that you need to put an extra instruction way up here in the beginning between these two, right? Well, if you do that, the address of all the following instructions changes. And if you had a go-to pointing to one of those, that go-to needs to go somewhere else. And so one reason for having no ops was just to leave space in your program so you could make changes later. That's not an issue with you know machines today because we have assemblers. We just write our code. If I put another statement in here and then I just reassemble, loop will change to another location, not a problem. The other reason we put in no ops though is just to waste time. And so we're going to develop a timing loop to do this 2-second delay. And sometimes if you had, a section of code that took a certain amount of time, it would be easy to turn that into like a 2-second delay. And so we'll add no ops just to change the length of a section of code inside a loop. And so that's the more...
To change stimulators too, like I do when I'm debugging.
Mm-hmm.
It's a great spot to just flip some switches.
Yeah, or to put a breakpoint, right? So yeah, they can be useful for development for reasons like that too. And you can always kind of fake a no op. I mean, you can move a file register to itself, but that changes the flags, and maybe you don't want to change the flags. You could move, a 0 into W, but that changes the value of W, and maybe you didn't want to change the value of W. So no op is just like do nothing, right? Just chew up 2 locations in memory, chew up, a certain amount of time, and that's all it does.
Thank you, by the way.
Yeah, you're welcome. All right, so let's take like a 4-minute break. Go ahead and send me an attendance ping. Let me know if you're here, and we'll come back in about 4 minutes. And the microphone is still on.
It's what?
It's still on.
It is, okay.
Yeah.
Can I, your white, please? I gotta have white. I can't do
It's
anything.
oil.
You don't have acrylic?
No, I have oil and I have water.
Alright. I have no idea. It's better than not painting.
Yeah. Or oil.
Oh, I don't even know the first thing about that, and that's complicated. Don't you have to clean that with turpentine?
Hmm?
Don't you have to clean that with turpentine?
No. That's got a little white. Got a bigger palette somewhere. White in the tube.
Yeah.
Yeah.
I think this will mix with mine.
Okay. Go for it, man.
Oh man, thank you.
Yeah.
Yes. This is coming out.
Okay. There's more colors for you.
Okay. Oh, thank you. or not?
Oh yeah, sure, definitely.
Yeah?
Yeah.
Okay.
Need extra brushes or anything?
Nope.
Okay.
That's all I needed was white. And
Okay.
I think that's gonna totally work.
And I have the magic water brushes.
Ah, okay.
Yeah. All right, we are back. All right, so let's talk a bit about instruction timing. And this subject gets a little funny since we're working entirely with a simulator, because the simulator doesn't quite understand time the way that the universe does. But what I'm describing is what would be happening if we had a physical PIC chip and we actually connected it to a proto board and were, doing experiments based on that. The simulator is supposed to let you do this, and the last time I checked, it did not work the way it was supposed to. So we kind of have to sort of take some of this on faith, and believe that it's doing what it's supposed to do. But let's just talk about the theory of timing on a processor. And you remember from 250 when we do state machines, right? Everything is based around the idea of a clock. And a clock just ticks up and down, up and down, up and down all day long. And it clocks at a certain rate, a certain number of up and downs per second, which is called the frequency. And the flip side of the frequency is the time that it takes to go from one, say, upward transition to the next. And that's something called the period. And period and frequency are related. The higher the frequency, the shorter the period. The longer the period, the lower the frequency. So they're reciprocals of each other. And the PIC processor is just a big state machine. It's a system that moves from one state to another based on what's happening to the pins, what the bit patterns are that are stored in the program memory and stored in the function registers. And so this state machine changes state each time that the clock ticks. All right. Well, the clocking on the PIC comes in a variety of levels of complication. Let me pull this out of the way. I don't think I have this on the quick data sheet. I think we got to go to the real data sheet. And it's either chapter 5 or chapter 8. Or maybe chapter 3. I should have marked this up. There we go, chapter 5. All right, so figure 5.4 and example 5.2. So there's a clock inside the PIC chip, and as soon as you apply power, this clock starts ticking. And if you don't do anything else, this runs with a frequency of 31 kilohertz. So 31,000 ticks per second. Right, and it's always ticking, on and off, high, low, high, low, high, low. 31,000 times a second. There's other clocks inside the processor. The fastest one goes at 8 megahertz, so 8 million high-low transitions per second. The default one you get is 31K. I have a bug in my code, yeah. And mostly we'll deal with the 31 kilohertz clock. So this oscillator one up here, this is the system clock. This is 31,000 times a second, or 8 million times a second, and so on. But we break up that system clock into chunks of 4 ticks. And it basically takes 4 of these ticks to do what's called a fetch cycle. That's grabbing an instruction from memory so that we can prepare to execute it. So what does the fetch look like, right? Here's our PIC chip. Here's the program memory, right? It's 21 bits wide, actually. Ours only has to be 12 bits because we only have 4K of instructions. But the architecture supports up to a 21-bit address, right, which is like 2 million bytes of instructions. So the program counter, which stores the address of the instruction to execute, is actually 20 or 21 bits wide. And that's used to access our program memory. And then the value of that instruction that's stored at that location in program memory, that gets processed, right? Something breaks it up. It looks at table 20-1 and says, oh, 00110. That's an increment instruction. And these 8 bits tell me I should be incrementing register 23, right? So this instruction decode and control is all complex circuitry that looks at those 16 bits of instructions and figures out what to do. So the process of fetching that instruction from memory, that takes 4 clock cycles. All right, we've got to take the program counter and send it into this memory, and then wait for the value that we've addressed to get selected, and then take that value that's coming out and save it somewhere. That takes 4 clock cycles. And then this block that looks at that and figures out what the bit pattern is saying and decodes it and actually does what the instruction is supposed to do, that takes another 4 clock cycles. So this picture here is basically showing you, here's the clock that's always ticking. These first 4 clock ticks are being used to fetch some instruction at the address of the program counter, and these next 4 clock cycles are being used to execute that instruction that was fetched. All right, so nominally speaking, it takes 8 ticks to do one instruction. But life is a little better than that. So we'll take a little side trip here and we'll talk about pipelining. And when you take a computer architecture course, you'll spend weeks talking just about pipelining and doing calculations on pipelined execution and stalls and all sorts of fun things like that. This is just a high-level view of it. And the example I like to use for this is doing laundry. All right? So let's say you want to do laundry and you have a washer. All right, there's my front-loading washer with a tiny little door. And you've got a dryer, you know, with a top that closes, so there's a dryer. And you've got a table that you use to fold, and then you've got, you know, some kind of cupboard that you use to store your clothes. As if anybody actually went through all these steps, I don't know. And let's suppose it takes, you know, 1 hour to do each of these. So your wash takes an hour, your dryer takes an hour. It takes you an hour to fold your clothes because you're very precise about it, and maybe you iron them while you're folding them. Then it takes an hour to store because you keep a spreadsheet on your computer showing where your clothes are, and it's all very detailed. Right? All right. So let's say you have one load of clothes to do. How long is it going to take you from start to finish to do one load? How much time? And it's not a trick question.
4 hours.
4 hours, thank you. All right, it takes an hour to wash, an hour to dry, hour to fold, hour to put away. It takes 4 hours to do one load. All right, now suppose you have 2 loads. If you've never taken a computer architecture course, and you haven't taken Engineering 270, you might try to do your 2 loads as follows. You take your first load. You put it in the wash, then you move it to the dryer, then you fold it, then you put it away, then you take your second load, you put it in the wash, put it in the dryer, you fold it, you put it away. 2 loads takes you 8 hours. 3 loads. While you do your 2 loads and then you do the third load, that's going to be 12 hours. All right? Can we be more efficient than that? Definitely, right? So supposing you have friends over, you convince them that this is a party, right? So you have one person who can take care of the washer, another takes care of the dryer, another folds, another stores, all at the same time. We can do these things in parallel. So we can make a pipeline. And the pipeline looks something like this. We put load 1 into the wash. And then when load 1 is done, we move load 1 to the dryer and we put load 2 into the wash. And then when an hour passes, load 1 can go to the folding station, load 2 goes in the dryer, and load 3 goes into the washer. And then an hour later, load 1 gets stored, load 2 is being folded, load 3 is in the dryer. And an hour later, load 2 is being stored, load 3 is being folded, and an hour later, load 3 is being stored. And this did not take 12 hours. It took 1, 2, 3, 4 hours to finish the first load, but after that, it only took an hour to finish the second load, and after that, it only took an hour to finish the third load. So if we have this kind of pipeline, it only took 7 hours. All right, so this is pipelining, and it's a way to exploit parallelism. The fact that the washer and the dryer are independent resources, and so we can be doing something with the dryer while we're using the washer for a different load or a different instruction. So on the pick processor, we have a pipeline that looks like this. The first part of the pipeline is the fetch. The second part is the execute. And the idea is, okay, so first we fetch instruction 1, and that takes 4 clock cycles. And then we go ahead and we execute instruction 1, but while we're executing instruction 1, at the same time, we're fetching instruction 2. And then 4 ticks later, instruction 2 executes, and we fetch instruction 3. And 4 ticks after that, instruction 3 executes, and we fetch instruction 4. And so it looks like every 4 clock ticks, another instruction finishes. And so even though the instruction actually takes 8 clock ticks to execute, we complete another instruction every 4 clock ticks. All right, that's the essence of pipelining. That's what makes our world work today. Our processors are deeply pipelined, and all of the hard work in computer architecture goes into making sure this pipeline works well. So this is something called throughput, which is 1 instruction every 4 ticks. But any instruction actually takes 8 ticks from start to finish. But the effective throughput is it only takes 4 ticks per instruction.
Isn't this similar to the wave timing thing we did in the last quarter?
What did we do in the last quarter?
Don't remember. I don't remember what it was called, but basically you'd adjust the timing to a 1 or a 0, and it would wave down. So by the time that you ended up to the 12th step, number 1 is at the first start, and 12 had how many other steps in it, and it just was in a wave form.
Sounds vaguely familiar, but I'm having trouble remembering the details of that. But it might have been something similar.
I was looking at my labs, but I couldn't put my finger on it. I was like, I don't see a picture of exactly what I'm referencing.
Yeah, but it sounds familiar. If you think of what it was, let me know. Because that would be a nice tie-in.
Sorry, what does that word say again? Below through instruction.
So up here.
The one beneath that.
So any instruction takes 8 ticks to execute. But the effective throughput is that each instruction is only taking 4 ticks to finish. In other words, every 4 ticks we finish another instruction, even though it's taking 8 ticks to do 1 instruction. So this is like an assembly line, right? You take a large amount of time from start to finish, but if you're doing it in pieces, you complete the process for each new output in a much smaller amount of time. So that's what you're seeing here is this this notion that you fetch instruction 1, you execute it at the same time that you're fetching instruction 2, you execute that at the same time you're fetching instruction 3, and so on. And so even though we have these clock ticks, which is 31,000 times per second usually, we usually talk about an instruction clock, which for us would be roughly 8 kilohertz. It's 1/4 of the actual system clock. And we think of an instruction cycle, which is 4 system clock cycles. So pretty much always in this course, I'm going to work with this 31 kilohertz system clock, 31 or 32. And when I talk about the system clock, I'll be talking about 31,000. When I talk about the instruction clock, I'll be talking about approximately 8,000 instructions per second. And when we talk about an instruction cycle, we mean, 4 of these system clock ticks, which is the amount of time we need usually to finish one instruction. And so now if you go back to hopefully everyone's favorite table, which is 20-1, where we see the synopsis of instructions, we can look at this middle column now, cycles. How many clock cycles, instruction cycles, does it take to execute this instruction? Well, an add WF takes 1 cycle. 4 system clock ticks, so about an 8,000th of a second. Move FF, well, it has to fetch 2 words. It actually takes 2 clock cycles. But most of these instructions take 1 clock cycle. But there's a few oddballs in here. Right, so a branch takes 2 clock cycles. A conditional branch takes 1 or 2 clock cycles. So why are branches different? Suppose you're doing your laundry, and suppose that you wash your first load, you wash your second load, you wash your third load, you're drying your second, you're folding your first, and suppose at this point you suddenly realize you're doing the wrong laundry, right? You picked up your housemate's laundry by mistake, and you're not doing the right laundry. Well, you discover it, while you're folding the wrong clothes. It's like, hey, these aren't my socks, right? Well, that means not only that the clothes that you're folding aren't the ones you wanted to fold, the clothes that are currently in the dryer aren't the ones you wanted, and the ones that are currently in the wash aren't the ones that you wanted. And so what do you have to do at this point? Well, hopefully, you would finish the laundry for your housemate. But if you're a ruthless CPU like the PIC processor, what do? You just chuck these. You say, get rid of that, get rid of that, get rid of that, and you start over. And you clear all of this stuff out, and you go back and you take the next load of clothes that you wanted to do, and you put them in the wash. And it's going to take 4 hours before that load of clothes is done. Okay, this is called a pipeline stall. It's also called a flush. You're flushing the pipeline out. You're saying, hey, all the stuff that's in the pipeline, that's not what I want to spend my time on. And you get rid of all of it, and now your pipeline is empty. And so the next instruction that you fetch is going to go in here, and you're not doing things in parallel anymore. Right, so you're starting over, so that first load's going to take 4 hours. So when you have a pipeline flush in a CPU, the next instruction takes 2 clock cycles instead of 1. And that's what's happening when you do something like a branch. Because when you do a branch, what happens? You start executing code from somewhere else in memory. And while you were executing that branch statement, you were at the same time fetching an instruction that's not the instruction you wanted. And so after the branch is done, hey, guess what? That instruction you fetched, not the one you wanted to do. So now you have to take the next clock cycle and fetch the correct instruction, and then the next clock cycle to execute it. So branches end up taking 2 cycles. They don't. They actually take 1, but the following instruction will take 2 cycles instead of 1. So we say this takes 2. And it ends up being the same. And then conditional branches, we don't know how many cycles they take. If you end up taking the branch, if the carry is set, and you're saying branch of carry, same thing, you're going to flush your pipeline, it's going to take 2 cycles. If you say branch of carry, but there's not a carry, you won't branch. The next instruction that you already fetched is the one that you wanted, so it only takes 1 cycle to do that conditional. So these things make your timing potentially funny.
So every time you need to use a branch, the next few instructions that it would have planned in the pipeline to do rid of them because you're moving the instruction pointer somewhere else.
Exactly. Yep.
Okay.
That's a perfect synopsis.
Same with call. Well, maybe not call.
Same with call. Yep.
Oh, it is? Oh.
Yeah, anything that changes your program counter to be something other than, the current value plus 2 or 4, something that causes you to not execute the next instruction in memory is generally going to cause a pipeline stall. Now, better CPUs will look ahead. They'll have a longer pipeline, and they'll actually look ahead and they'll say, 5 instructions from now, there's an unconditional branch. And so they'll see that and they'll start branching from the correct location, start pulling from the correct location ahead of time.
Oh, so that's why they have branch prediction.
Yes, because...
So they don't need to flush the whole pipeline. Okay.
Because if you can tell the future, before you get to this branch of carry, if you can predict whether or not that branch is going to happen, you can proactively start fetching from the correct location. But you need a crystal ball. You need to know when I get there, is this branch going to happen or not? And that's hard to do, right? Maybe you're going to do something like, x equals, some big long function, and then if x is equal to 0, call something. Well, until you've done all of these calculations and figure out the value for x, you don't know if it's going to be equal to 0 or not. But the CPU has a little genie inside that'll try to predict. And the genies have gotten really good. And so they look at statistics each time that you get to this section of code and say, most of the time when you get here, this is not 0. I'm willing to bet you're not going to make that call. And it'll keep fetching from the next locations in memory. Or it'll say, most of the time when you get here, you do take a call, and it'll start fetching from that location in memory. And a lot of the hardware in a CPU is built around this idea of branch prediction. Because if you can predict correctly whether a branch is going to happen or not, you can keep the pipeline full. And a full pipeline, that's what makes or breaks your business. Right? So if your pipeline is 10 steps long, you can get effectively 10 times as fast an execution. Right? If your CPU is clocking at a gigahertz, theoretically, if it's a RISC machine and it takes 1 cycle per instruction, you're doing 1 billion instructions every second. Until you hit a pipeline stall. And if you have to flush the pipeline, now you're down to 100 million instructions per second, 1/10 the speed. So the degree to which you can predict these flushes and avoid them corresponds to how meaningful that clock speed is. If you get a 3 gigahertz CPU, does it really do 3 billion things a second? Well, depends on the architecture, depends on the operating system, depends on what you're doing with it.
So, if we want to avoid the pipeline stalls, because if you think about the memory hierarchy, it takes, some 60 instructions for the CPU to actually get a thing from the memory to the cache where it will execute something. So we're trying to avoid having to pull stuff from memory so we can just keep executing stuff over and over and over again.
Yeah, so fetching from memory is usually pretty slow. So prefetching is the way to avoid memory delays. And so you grab the stuff ahead of time. And this gets into like cache memory and levels of cache and all that sort of stuff. And computer architecture class, you break that all down, and it's pretty fun to sort of see how all those things work. So it's all related. All right, and let's see, simulation waveform for the shift register in Verilog. Yeah, so similar idea. In the Verilog labs where we were making a shift register, things were moving from one flip-flop to the next each clock tick. Same idea, right? And that would be a fun lab, actually, is like model a pipeline system in Verilog. I won't do that to you. All right, so we've got about 15 minutes left. Let's jump into Lab 3. And a lot of what we've been talking about with the pipelining and stuff like that is conceptual stuff that will help with, using this information, but this is, you know, not a computer architecture class per se. That's part of the curriculum. But, you know, mostly we're interested in understanding these concepts well enough to be able to use them to write code and make delay loops and, you know, traffic light controllers and things like that. So you know, definitely think about these things, but don't panic if it's, you know, kind of nebulous, because, you know, we could spend a week talking about we could spend, you know, 3 weeks talking about pipelines. We're just kind of doing first order. All right, so let's look at lab 3. So lab 3, pretty straightforward to describe, right? It's a traffic light controller. We all know about the traffic light labs from 250. This is the same setup. It's a single experiment. And you know, we're using the default oscillator, which is 32 microseconds. So that's the 32 kilohertz clock. And then 128 microseconds, that's the 8 kilohertz clock that we have for one instruction cycle. So the instruction cycle is 128 microseconds, or an eighth of a millisecond. All right, so there's sample code in here, right? Most of which you won't end up using for your traffic light controller, but this is mainly playing around with a delay function. So, you know, boilerplate stuff up here. Here's your main program starting at origin 0. Sets up adcon. Sets up trisb bit 0 to be an output by clearing that bit of the tri-state register. And BCF is a separate function. We haven't talked about that yet. We'll go through those later. But it's setting up tri-state B. We could just clear tri-state B if we wanted. So what does this program do? It toggles bit 0. So bit toggle is you know, saying if the bit's a 0, change it to a 1. But we could, you know, do something else in here. The main thing to pay attention to is it does the following. It puts a 20. So period 20 means this is a decimal number, right? 0x20 would be hex. B quote would be binary. Putting a period in the front makes this thing a decimal number. But it's not 0.2, it's actually the decimal number, 20. So it puts 20 into W, and then it moves that into this file register called dcount, right, which is set up at location 80. And then it calls this function delay. All right, what does delay do? Delay looks at the value of dcount, and it waits that many tenths of a second. So if I put a 20 into dcount and I call delay, I should end up spending 2 seconds in this delay routine before I return. And then when I return, I come back here, and I'll branch back to loop, and that will toggle bit 0 of my port B. So if my LED was connected to bit 0 and it was off when I toggle it, it'll turn on, and then this call will wait 2 seconds. And then I'll go back to loop, toggle it, my LED will go off. So this code would cause an LED to turn on and off every 2 seconds. The reason that this is interesting for lab 2 is really just this routine right here. So this delay routine puts 195 in the W register, makes a little loop that decrements it, and branches back here until it decrements to 0. So it does this loop 195 times. And that takes a tenth of a second. And we'll dig into that on Tuesday and see why that is. But for now, you can just use this code verbatim. And then after that tenth of a second, it decrements this counter that we loaded with 20 in this case. And if it's not 0, it goes back and it does this again. So this whole loop from here to here spins for decount iterations of this inner loop. And this inner loop takes a tenth of a second. So 2 things to take away from this, right? The first is this function called delay that you can call, right? Load a value into decount and then just call delay.
Sorry, I have a quick question.
Yeah.
So branch it not zero, it's the last operation. If it resulted in a zero,
Mm-hmm.
not doesn't affect the zero, right?
Right, if you look at the instruction table, NOP does not change any status bits, so it's actually the status bit from this decrement.
So you can stick one there and it still works, okay.
Yeah, exactly. And so if you're debugging your code, this is going to run, if you ask it to wait 20 seconds, this is going to run 8,000 times, right? So load a different value into here. Load like a 2 into W instead of 195, and you get a much smaller timing loop. All right, so we'll break that timing loop apart in detail on Tuesday, but for now you can just kind of use this as is when you want a 2-second delay. Or, just make a dummy function called delay and just put a breakpoint there so you know when you've gotten there and just have it return. But, when you get to that breakpoint, okay, it's going to spend 2 seconds here and then return. So the lab itself, right? 3-way intersection, west, south, east. Please label them west, south, east, just like in 250. Don't label them A, B, C, or 1, 2, 3. W, S, and E for west, south, east. And we have some sort of sensor that tells us if there's a car on each of these lanes. And we have a light. And each light has 3 lights to it. Red, yellow, and green. And you want to write basically code that looks at these sensors and adjusts these lights accordingly. And same as 250, east is highest priority, then south, and then west. And if there's a car to the east, east should be green. If there's no car to the east but there's one to the south, south should be green. Otherwise, west should be green, and everything else should be red. But then when priority changes, whoever has the green light should go yellow for 2 seconds, and then go red, and then whichever is the highest priority should go green. So it's like the final version of the 250 traffic light setup. So the 3 car sensors, west, south, east, come from RA0, 1, and 2 respectively. And the 9 lights corresponding to the west, south, and east, green, yellow, and red, come mostly from port B, with 1 bit coming from bit 7 of port A. So this table tells you which bits of which ports correspond to which light. And your goal is to just make a big loop that runs forever and basically monitors the sensors and adjusts the lights accordingly. All right, specific requirements for this lab. So, again, it says pseudocode, but I want to see a flow chart. Okay, I'm always going to ask for a flow chart, but I recommend starting with pseudocode, and we'll spec out some pseudocode here in the final minutes. But definitely include a flow chart. Definitely include a test plan. So how do you plan to tell whether your code works or not? Well, you're going to set up some stimulators, and you're going to, set up this collection of sensor inputs, and then you expect to see this result on port A and port B's outputs. And then you're going to change the stimuli to set up this combination of inputs, and you expect to see this behavior where this turns to yellow, and then this is going to happen, right? Detailed test plan. So that somebody else who takes your code can go through the same steps that you've described and confirm whether or not the circuit is doing the right thing. All right, and for this one, you definitely want to include simulator output. So what kind of output should you have? Well, you don't have to go through, how you set up the stimuli, and I click this window and put in a new watch and so on. But you want to show the effect of executing your code. So, start off with, I don't know, maybe east has a green light. So make sure that you have a screenshot that shows the values of port A and port B, and, put a comment below that in your report that says, the current value of port A is this, port B is this. That means east has a green light, south and west have red lights. Next, we stimulated the south car sensor, right? So go ahead and hit that stimulus and step the code, and you should see a change in the input pins, right? do a screenshot that shows the value of port A where the inputs are coming in, and put a note down there saying, you know, bit 1 is a 1, indicating there's a car to the south. And then step your code through until it changes the eastern light to yellow. Take a screenshot, put a note. At this point, the eastern light has turned yellow and our code has just entered the delay loop. Alright, now you can't do a screenshot to show that 2 seconds have passed, right? But you can put a note at that point in your lab which says the delay loop takes 2 seconds because, and put in your calculations there, which we'll go through Tuesday, right? Saying this, you know, does 8,000 executions, you know, per second and so on and so forth. And then when you come out of the delay and you keep stepping through your code, you should get to a point where east has turned red and south has turned green. Take a screenshot, put a description of that. At this point, port A has this value, port B has this value corresponding to, you know, south is green, west and east are red. Right? This is a lot of work to write up. Okay, this is not going to be a 4 or 5 page lab write-up. So plan accordingly, right? Get the work done early. Make sure you understand that it's working correctly, and then plan on spending a good amount of time actually writing it up and presenting it. And again, keep coming back to the idea, can somebody take what I've written and reproduce my work? Can they confirm that these are the results? Does that make sense? Yeah, it'll be okay though. It's and it's really fun once it works. It feels like you know, the major thing that it is. It's a really cool accomplishment when you actually start stepping through this and you can see, you know, traffic light behavior. And yeah, cool comment on time units in simulations or game engines. It is the same thing, so yeah, that's pretty cool. All right, got a few minutes. Let's think about pseudocode for lab 3. There are a lot of ways you can do this, but let me just get you started with a possibility for thinking about lab 3. So you're going to do a bunch of setup. You're going to set up trisses and add cons and all of that stuff. But the main guts of our loop can be something like this. So if there's a car on the west, right? West is the highest priority. Okay. Imagine keeping a variable which shows who had priority last. So I'm just going to imagine a variable called priority. I'm going to set it equal to either south, west, or east. You're going to have to use numbers for this or bit patterns or something because it's assembly language. But at a high level, right, I can think of this variable priority which says, you know, west, south, or east is currently the highest priority. Okay, so my main loop can do the following. Check to see if there's a car to the west. And let's suppose there is. Okay, so I've got a couple of possibilities. If my priority, if the car that had priority last was south, well, that's got to change now. If the car on the south had priority, it means south had a green light. But since they got a car on the west, west should get priority. So if the last car that had priority was on the south, what do I want to do? Set south yellow. Wait for 2 seconds. Set south to be red. Set west to be green. And remember that my priority lane is now west. All right. Well, there's everything we need for that one condition where south had a green light, but a car showed up to the west. If there's a car on the west and south does not have a green light, but east did, Well, kind of the same thing, except here we set east to yellow. Wait for 2 seconds. Set east red. Set west green. And remember that our current car with priority is to the west. That's pretty much all we have to do if we see a car on the west.
I thought east had highest priority.
You are right.
Okay.
I should have drawn my little picture. Thank you. No, that probably saved a lot of people and myself a lot of time.
It's a lot of if statements.
Yeah, it is, which is going to be really good practice for getting good at conditionals. All right, so this is all if there's a car on the east. If there's not a car on the east, and I want to have an else here, this has got to be an else, right? The way that I'm doing it. Else, if there's a car on the south, well, we know there's not a car on the east, right? But if there's a car on the south, well, if priority is currently given to the east, set the east yellow, wait 2 seconds, set the east red, and then set the south green. If priority is to the west, set the west to yellow, wait 2 seconds, set the west to red, and then set south to green, right? So do all of those things. Else, and if there's no car to the east and there's no car to the south, I'm just going to say give west priority, whether there's a car there or not. So then in that case, right, we're going to give west priority. So if there's a car on the east, set it to yellow, wait, set it to red, and then make west green. If there's a car to the if south has priority, set it yellow, wait 2 seconds, make it red, and then give west priority, make it green.
Are we supposed to do it that way, or
Nope.
are we supposed to set all three to red if nobody's there?
It's up to you. It's totally up to you.
Okay.
If it's easier to set all three to red, I'm okay with that. And this is not the only way to structure it. This is one way, right? There's a lot of different ways, but this is one possible way, right? And it can feel like a lot of code, but we're doing a lot of the same things again and again and again, right? And when we need to do something like, you know, set west to red and set south to green, think carefully about what that looks like. If you look at the output values here, well, if we want to set, you know, west to red and south to green and east to red, well, that's just a particular bit pattern we want to write to port B and port A. We want a 001, 100, 001. Well, I could make a function, you know, for setting each light to a particular color, right? I could make a function called west green that'll basically write a 100, 000, I could make another function for west yellow, which would put a 1 here and zeros everywhere else. And if you're careful about this, you only need like 6 possibilities. Either west, south, or east, or green, or west, south, or east, or yellow. So this is kind of like when we talked about doing this controller in Verilog with a state machine. If you spend more time thinking about how you're going to organize this up front, you may spend less time with the actual coding, and then less time debugging. So spend a while thinking about this. And this, you know, kind of high-level breakdown of it, that's a really good thing to collaborate on with friends, right? That's something I'm totally cool if people want to kick around ideas, because there's so many different approaches to it, right? But then when you start actually trying to turn this into actual code, that's got to be your own work. And guarantee you're going to come up with your own code, even if you're starting with the same basic algorithm. So think about this. Figure it out at this level. This should be where you spend most of your design time. And then go ahead and flowchart it. And that will help you figure out where you're going to do your conditional branches and so on. And then get down to the level of, well, how do I set south to yellow? Well, I have to put a 0 in this bit and a 1 in that bit and so on and so forth. And like I say, for delays for now, you can either just call that delay function with a smaller value of w, or just hit a breakpoint. You know, call a function, put a breakpoint there, and then every time you get there, you know that you're doing a 2-second delay, and then go back. And then Tuesday we'll go through some more details of that delay function. All right, is that enough to get going?
Yeah.
Cool. All right. Send me one more attendance ping to let me know you're still here, and I will switch into my office hours and catch you in there. And if I don't see you in there, have a great weekend, and I'll see you next time.
Have a great weekend.
Thanks.
Good weekend.
Appreciate it.
Thanks.